So I come from Bologna. I'm at the University of Bologna. And this icon here is Virtual Square, which is a team which is developing solutions, tools, ideas in the field of virtualization. VUOS, give your processes a new view. View, it's not an acronym. It must sound like view. So, which is the point? What a process can view? A process running on an operating system is able by itself to execute machine operations. It's able by itself to access its own memory, but everything else must be obtained through system calls. So the environment, the view, the panorama that the process is seeing outside its world, it's given by the answer, by the reply that the system calls gives it back. Okay, so namespaces in the kernel are ways to provide processes with different views on a file system, different views on networking, different views on process IDs, user ID, or whatever. What we are designing with VUOS is something similar, but completely developed, completely running in user space with just user permissions, without the need to be root. This can reduce dramatically the attack surface, because we don't use namespace feature in the kernel. So you can imagine to run a kernel with the namespaces disabled. And at the same time, we provide solutions that are available to standard users. Nowadays, it happens so often that solutions, tools are provided for system administrators. But that it means that it's another way to enlarge the attack surface, as faulty programs, bugs, can create damages to the system. So, what the idea starts, the idea comes from a need. Why it is not possible for a user to mount a file system? If I have a file system image, it's a file of mine. So mounting a file system image and changing the contents of the files included in that file system image once mounted is just a sophisticated editing of a file of yours. Why is it forbidden in a standard system? Just because the idea of mount is an idea of a global operation of the system. This operation either is provided as a global operation, as in the past, or is provided just to a subset of processes, but by the kernel in namespaces. Instead, it must be possible to mount file systems as users. In this presentation, I want to show you first what and why, and then at the end, how. The reverse way around. So, which are other applications? I can need a virtual device. So I want to create a RAM disk for my application. So if it's a RAM disk for my application, why I need to pre-root? Why I need to need the kernel services? Or I want to use a different network stack. Or I want to see a file which is here, there, like the bind mount. Or I want to remount the entire file system in cow mode, in copy and write mode. I want to change the name, the time, user ID, whatever. But I want to do everything in user space, user permission. So instead of, I have slides with demo, but I prefer to provide you with a demo. Reset. Here I have a file system image. I would like to do this. Because this is the natural way to mount a file system. Actually, I get from the kernel, actually not from the kernel, this is an error of the tool. It's the mount tool that say you're not root. This is an error of the tool. But even if you try to call the system call, you get the error. How can you do that? You start a VUOS machine. This window is running inside the machine. Again, if I try to mount this, I get the error. But if I add the module to provide file system virtualization and mount this just saying the type of file system, and as a workaround to the mount command error, I have to use view mount, which is a mount. You can use view mount to mount everything else, but it tries the system call. Wow. What is nice about life? Okay, the problem is that, okay, now I have mounted the file system, but just for this. Okay, actually this is mounted, but this is another file system, as you can see. So I've mounted my file system over there. This is just an example. Okay, let us start another virtual machine. I have here some commands to be. Okay, let us this time, if I can pick up the command, I add two modules. One is for virtual devices, one is for virtual files. And with this command, I create a virtual device named dev RAM disk, which is a RAM disk 100 megabyte large. So, as a user, I can create a file system on a RAM disk. Then I can mount the file system And now on /mount, I have the new file system, which is into the RAM disk. I want to point out that I'm using the commands that I use as an ordinary system administrator outside the virtual machine. So one of the goals of the project is to use the natural commands to do what you need. Let us go further. This is a common problem I had. I always forget the commands to loop mount partition of file system image. For example, if you have a Raspberry Pi, the image has two partitions. If you want to mount one partition to change one file, it is a mess. And second, you need to be root. Now I'm showing you how to access the partition of a Raspberry Pi image as a user. So again, I add the two modules. Now I use another virtual device module, which is partix. And as you can see, that's an image I've just downloaded from Raspberry Pi site. And now I have in /dev/sdx my disk. So I can okay. I'm not root, so I need you can see the partitions, okay? And given there are STX1, STX2, I can mount STX2. So I can mount the second partition. Here I have the root, the root partition of the Raspberry Pi. I could change the file, do whatever I want. Or let's continue. Okay. Now let us play with another toy, networking. The model for networking is VUOS. Now, let me try. Okay. Let's try this experiment. This is quite a new development. It's already unstable, but I want to. There's a development. I have created together with Daniela Camera. This is PicoTCP as a user mode stack in VUOS. And given that PicoTCP is connected to VD networking, I've used it as the networking interface SLIRP, which is the tool used by virtual machines to provide user-provided networks. Now, we provide in VUOS different stacks at the same time in order to change to decide. And you can see I've mounted the stack in DevNet Peacocks in order to say I want to use that network because now I have my interfaces. But if I say view stack, I open a bash, and in this bash, I have the PicoTCP interfaces. It's a choice. PicoTCP uses a hash it is. So it's quite different from standard networking because usually you have the name, the number of the interfaces 0, 1. We have but now I can self-configure the network using a standard DHCP client. Okay. Now I've got the address, and again, this is my machine, my computer in Bologna. I've used the stack in the virtual environment. Okay, final demo. This is the current time. Now I can start a VUOS machine. And now I start another submodule, Mish. And this time, and I start another X-clock. Now I mount, let me move this clock, which is now I mount the module VUMISH timing mount, and it is like a proch file system. So mount contains some fake files, and I can use this to change the view of the process regarding time. For example, if I put 2 in mount frequency, as you can see, we have relativistic machines. So the time in the virtual machine runs twice as faster as the time in the normal life. Okay, so as you can see, this the idea of VUOS is providing means to provide the processes with the view we need to solve problems. So we have started from the solution. We have started from what is useful. Now I can show you okay, all the demos I've done now are in the slides, so you can test by yourself, if you like, all the demos after the talk. This is the structure of the OMView, which is an implementation of VUOS. We can provide further implementation in the future. There are processes in the user space, and there is we use system call interposition to decide which system calls must be forwarded to the kernel in case you are accessing part of the system which are real, or the system call are completely implemented in the hypervisor code. In order to have them to achieve the better results with parallelism, we use a technique that we have named guardian angels. So each process running in the user space has in the hypervisor a thread which is providing the virtualization for that thread or process. So each process in the user space has a guardian angel thread in the hypervisor. So if a process runs an open, the guardian angel tries to see if the path is in a real or in a virtual part. If it's the real part, it simply says the process forward the call to the kernel. Otherwise, the guardian angel and the model choice is for the choice of virtual or real, and in case it's virtual, it returns the module which is responsible for the virtualization. Okay? So, the system call, there are wrappers that get from the user memory all the parameters, what is needed to perform the virtualization, and the system call is forwarded to the module. We have seen in the demos Fuse, DevNet, and the implementation of file system, networking, or devices, or whatsoever, really perform the actual action to have the result. I have 2 points to note now. One is I have, in an example, I have created a virtual device, and inside the virtual device, a virtual file system. So this was a nested virtualization. So try to think that we open a file in the virtual file system. That call is forwarded to VFuse for the virtualization of the file system. How can we achieve the virtualization of device on this? The hypervisor uses a self-virtualization method. PureLibC is an overlay on libc that is able to to catch all the system calls generated by the process itself. So even the read or write from VFuse is returned to the choice function, and if it sees that there is a further virtualization in place, it calls in this case, the device virtualizer, and for example, for the RAM disk, and it provides the correct answer. Let me point out that the interface to the modules is clean, simple. Let me see, KISS. Keep it simple and stupid. The modules receive just the system calls. So if there is a read here, read file descriptor, buffer length, over there the module receives a read, file descriptor, buffer length. Okay? So a module is simply created by registering the service to the hash table. So one module can register, I am responsible for this subtree of the file system, or I am responsible for that file, or I am responsible for that address family, I am responsible for that or the other system call. And then it has to provide the implementation of the system call. If somebody want to access that kind of file, so there is a read, what must be the answer? That's all. Okay, I have no time to show the code, but everything is available. We have a wiki site. We are redesigning the wiki site. The most important here is the set of repositories, and there is actually an infrastructure for a tutorial. We provide we provide a disk image and scripts to make it easy for whoever want to try the tools to have the whole infrastructure ready to perform the experiments I've done 5 minutes ago. So feel free and please download the image, try the tools, and if you like, if you want to participate, the project is open to all contributions. Thank you.
So we have time for maybe one or maybe two quick questions.
How do you compare VUOS with GUIzer or user mode Linux?
Sorry?
How do you compare VUOS with GUIzer?
User mode Linux, I compare user mode Linux to VUOS or UMU. User mode Linux creates a complete virtual machine, so it boots an entire kernel. We don't boot anything. We just put the system in a condition to grab the system call and divert the execution of the system call to modules if required. So 2 points. Oops. Okay. We use BFS to accelerate the grabbing the system call catching. Now we can do just avoiding the second call. Each time a system call is grabbed by ptrace, you receive 2 calls, one before and one after. So using BPF now we can avoid the second call, whether the system call is completely real or completely virtual. We have system calls that are at the same time real and virtual. For example, open. We have a virtual open, but at the same time we force the process to make a real open because we have to allocate a file descriptor. Okay. We would like to offload many parts of the decision process in the kernel, but we would need eBPF with seccomp, which is a long discussion in the Linux kernel mailing list. So if you are interested and you like the project, help us to convince the Linux kernel mailing list to add the eBPF for the seccomp system call.
Okay, I think we're at the end of this DevRoom today. Thank you for everyone who participated. Thanks.
Thank you.